Okay, I'm Dan Smith. This is my anatomy brief for Lloyd Dean. I'm on the development coaching and fitness course. The time is 18:07 and the date is 11th of the 4th 2014. I've decided to start with the respiratory system. Right, let's get started then. On the start, we've got the alveoli. Alveoli is located at the bottom, down here. And you can see like here, not very clearly, but they're like little walls. They are where the gaseous exchange will happen. Next, you've got the epiglottis. Epiglottis is this little flap here. It is there for the reason that the wind and the food don't go down the same pipe. The bronchioles, they are located here next to the alveoli. What the alveoli are attached to. Next, you've got the pharynx. The pharynx is this little tube here, which is straight, which leads all the way down. Then have the larynx, that is the next little stage to it, right here. Then the trachea, the rest of the tube. You then have the diaphragm. The diaphragm is from the lower chest upwards, as you can see, located just below the lung. Then have the bronchus. The bronchus is what the bronchioles are attached to, which you can see here. And finally, you've got the nasal cavity. Nasal cavity is where the oxygen we find will be coming in, and the CO2 will be going out. Okay, moving on to the heart structure next. First off, we've got the aortic valve. The aortic valve is located just here and here. Its function is to open when the left ventricle is full to allow blood to be sent out the aorta and around the body. Next, for the atria, which is located right here. We then have the pulmonary artery. The pulmonary artery is located just here. Its function is to transport blood from the heart to the lungs. How it does that is by it extends from the right ventricle, then leads off to the lungs to then become oxygenated blood. Then after superior vena cava. Superior vena cava is the taller bit of it, or the higher bit of it. Right about that. Its function is to bring deoxygenated blood from the upper region of the body, such as the head and the neck, and then to deliver it to the right ventricle, which is this bit here. The inferior vena cava, which is the lower part of it, that function is to bring deoxygenated blood from the lower part of the body to the right atrium. The pulmonary vein is this purple strand here coming out there, and the pulmonary vein its function is to carry oxygenated blood from the lungs to the rest of the body. No, sorry, to the left atrium, for then the left atrium to pump it out to. Then the bicuspid valve. Bicuspid valve is here. Bicuspid only has two valves, that's why it's bicuspid. That is because on the left side of the heart is not as big as the right hand side, so the right hand side can send more out to the body. The aorta is located up here. The aorta's function is to carry oxygenated blood to all blood vessels, and then when it is delivered to the muscles around the body. The aorta structure is made of a smooth muscle tissue, because it is hollow and blood has to flow through it easily to ensure that the muscles are getting the required amount of blood that they are after. Then you've got the ventricle. Here's one ventricle and here's another. Here's where the ventricle is. You've got the right ventricle and the left ventricle. Click on that. Okay, so to start off with the left ventricle. We've got that. Its function is to fill with oxygenated blood from the left atrium, and then when it is full, the aortic valve is open to allow blood out. We've got the tricuspid valve finally, which is here. That's got three, like I said before, for the more of the blood to go out to the rest of the body, and because the right hand side is bigger, it also will prevent any backflow of deoxygenated or oxygenated blood back into the heart, which would cause any harm. Okay, so this is kind of carrying on from the respiratory system. It's moving on to the lung structure. We'll start off with the lobes up here. As you can see, the lobes are separated from these black lines on here. There's the left lobes, 1, 2, and the right 1, 2, 3. Okay, so on the right lung has 3, and then the left lung has 2. The right lung is slightly bigger than the left, so this is the only reason that it has 3 other than 2. It helps the respiratory system through each lobe receiving air from this bronchus, and it is separated to the connective tissue. But in this case, my athlete that I've chosen is gold medalist Usain Bolt. So if you're using a lot of oxygen, needs to breathe in, Usain Bolt wouldn't need this, as he would just need to be powerful with when he's running for the 100-metre sprint. The advantage of having the lobes is that if one gets damaged, then the others can still function, but the person can still breathe normally. So everything should be alright. And then the next bullet point is the pleural membrane. The pleural membrane is a doubled layered serous membrane found in the thoracic cavity. The outer layer is called the parietal pleura and lines the thoracic wall. The inner layer is called the visceral pleura and covers the lungs. They produce lubricating serous fluid that causes them to adhere closely to one another. So it helps hold the lung to the thoracic wall, allowing easier movement during breathing, as the diaphragm will be moving up and down. The pleural membrane helps keep the two lungs away from each other and airtight. Therefore, if one lung is punctured and collapses due to an incident, the other pleural cavity will be airtight and the lung will work normally. So this helps us in everyday breathing and also helps us through physical activity. We then got the visceral pleura. It's the lungs are surrounded by the two pleural sacs. The outer pleura is attached to the chest wall and is known as the parietal pleura, as I just spoke about. The inner one is attached to the lung and the other visceral tissues and is known as the visceral pleura. In between the two is a thin space known as the pleural cavity or pleural space. It is filled with pleural fluid, a serous fluid produced by the pleura. It's a thin layer of serous membrane tissue that sticks to the surface area of the lungs. The visceral pleura is attached to the lung and other visceral tissues. Then moving on to the pleural fluid, it is found in between the pleural and visceral pleura. It's filled with the pleural fluid, a serous fluid produced by the pleural. This fluid then lubricates the pleural surfaces and allows the surface tension that keeps the lung surface in contact with the chest wall. It prevents separation of the two pleural layers and lubricates the surface so the lungs can move easily within the thoracic cavity. So this is again something else for when the diaphragm is moving up as you breathe in and moving down as you breathe out. Okay, and then finally we got the internal and external intercostal muscles. These muscles are found in between the ribs, the internal being on the inside and the external being on the outside. These are the muscles that help with the expanding of when the diaphragm, so when we're breathing in and breathing out, this is the thing that helps it. They wrap around the back of the rib almost to the end of the bony part of the rib in front. During inhalation, our external costal muscles contract and the internal intercostal muscles relax together with the movement of ribs and the thorax. That increases the volume of the thoracic cavity. The internal and external intercostal muscles will be key to such as a marathon runner, such as Mo Farah. But because my gold medalist is Usain Bolt, this is something again not so much what he's requiring, but he could still be doing with the oxygen to ready his muscles at the start of during the warm up. Okay, what you're seeing here is a picture of the alveoli, which is carrying on for the respiratory system. This here is where the gaseous exchange will happen. Gaseous exchange is of the oxygen that we breathe in and the carbon dioxide that we breathe out. During gaseous exchange, diffusion occurs as the blood in the capillaries surrounding the alveoli has a lower oxygen concentration than the N alveoli, which has just been inhaled. The blood which is surrounding the capillaries has a higher concentration of CO2, carbon dioxide, than the inspired air due to it being a waste product of energy production. The carbon dioxide will then diffuse the other way from the capillaries into the alveoli, where it can be then exhaled. As my gold medalist I chose being Usain Bolt, this is only going to be important to him for when he's doing his warm-up. As his warm-up he may just do some dynamic stretching and a light jog. This will be needed for the oxygen to get to the working muscles during that light jog and during his muscles to get them ready and to get them into a better shape. Then looking at this is the picture of what we've just done through the diagram. Looking back at this is now how I'll explain to you the mechanisms of breathing, so inhaling and exhaling. As breathing occurs when the contraction or relaxation of muscles around the lungs changes the total volume of air with the air passages inside the lungs. Inspiration occurs when the diaphragm and external intercostal muscles contract. Contractions of the diaphragm lead to an increase in the thoracic cavity, while then contraction of the external intercostal muscles, which are found on the outer side of the rib cage and sternum. Both these muscles cause the lung to expand, increasing the volume of internal air passages. Therefore, the air pressure inside the lungs decreases below that of air outside the body. Because of diffusion, air rushes into the lungs. Expiration occurs when the diaphragm and external intercostal muscles relax. In response to this, the elastic fibres in lung tissue. The air rushes into the lungs. The expiration occurs when the diaphragm and external intercostal muscles relax. In response, in the elastic fibres in lung tissue cause the lungs to recoil to their original volume. The pressure of the air inside the lungs then increases above the air pressure outside the body, and the air rushes out during high rates of ventilation. Expiration is facilitated by contraction of the expiratory muscles, which are intercostal muscles, and the abdominal muscles, which will be for when Usain Bolt is performing, to help with the mechanisms of breathing that are essential, as he will be needing oxygen, but mainly for the warm-up, not for the actual event. Then also with the lung volume makes up with the tidal volume, the vital capacity, and the residual volume. Your tidal volume is the air inhaled and exhaled at each breath, and is the amount of air exhaled after the person takes a normal resting inspiration or inhale. Your vital capacity is defined as your total amount of air that a person can inhale and exhale after a maximum inhalation. Your residual volume is the amount of air left in the alveoli in the lungs after a maximum exhalation. This residual inflation greatly reduces the amount of work required to completely re-inflate the lungs during the next cycle of inspiration. Both vital capacity and residual volume together can contain the total lung capacity. Vital capacity and residual volume equals total lung capacity. That's how we've broken it out. With Usain Bolt, he would have a larger lung volume, as he is a professional athlete and does not smoke and eats things right, keeping himself very fit. Also, if you live at a higher altitude, then you have a larger lung volume. This is going to help Usain Bolt, as it can help get oxygen to the working muscles quicker. But in this situation again, he's not going to actually need it because he's actually working aerobically, but to get the muscles quicker, to ready them for the explosive action he's going to be ahead, will be a greater advantage. And finally, for the respiratory system, we've got the control of breathing, neural and chemical. Neural control of breathing is when the brain controls breathing, so it's when you don't have to think about it when you're breathing. It helps happen through the brainstem. If the nervous system control of the muscles used in respiration, including the diaphragm, is controlled by the brain. The rate of breaths per minute is controlled by many factors, such as acid-base balance, the pH of the blood, and is part of the chemical control of breathing. You have the chemoreceptors, which are nerve cells. The body contains both direct and distant chemoreceptors all the way around the body, and they play an important role in every day-to-day bodily function. The cells are sometimes known as chemosensors because they have sensors which can detect for specific chemicals of anything or any nature or of any kind. Like other neurons, these cells are usually designed with custom locks which only fit the keys of specific chemicals, which are the ones that can only make them sensitive. Okay, we're now going back to the blood vessels. I'll start you off with the arterioles. The structure of the